Cool, I'll start. So my name is Brian, and I was on the New Zealand IMO team for like the past 3 years. And I'm supposed to start with a speech about, why mass Olympiad is good, right? So I guess yeah, I went to the IMO 3 times. It's really fun. I get to meet cool people like Dawn Haotian, who invited me to be the guest speaker here. And yeah, oh, you get to go on like free overseas trips. Like I think next year it's in Australia, and next year it's in Shanghai. So like free overseas trips. Also obviously you get to meet cool people. Um, yeah, and I know it might sound a bit distant and inapproachable, but it's actually we're actually going to solve one problem from the IMO today. And when we're done, you'll all see how approachable it is. So yeah, don't be scared. Mm, yeah, and even if you don't make into the team, it's fine because there are a lot of takeaways from Mass Olympia that's probably also quite valuable that applies to people who don't even need to make it, who don't actually make it into the team. Like I think thing for me the most important factor is how uh, how it provides me with a new courage. It's the courage of going up against challenges, challenging problems that you thought you couldn't solve before, and also the courage of changing your mindset, realizing that you're wrong, and trying to improve from there. All right, that's my speech as the guest speaker. I will now reenact my role as the substitute teacher and go through the handouts. Um, all right, so I'm thinking the format of this lesson is probably going to be I give you 2 minutes to work on the question, and then after 2 minutes, I will start asking for initial ideas. And after 5 minutes, I will give you start going through the solution. Is that fine with everyone? Cool, let's do that then. It's 6:37 right now. I will start asking for ideas. Oh, actually, let's skip question one because I don't like it. I don't like the look of it. Let's just start with question two. Yeah, starting with question two, I will start asking for initial ideas at 6:39. Have fun. Okay, 6:39. Does anyone have initial ideas? No one? Okay, I'll start picking on someone. Uh, oh, this person has a cool name. Snowflake, Lightning, Amonet, Fire, Wind. Uh, can you like contribute? Do you have any ideas in mind? Oh, oh, there's the chat. Okay, I probably should check the chat. Liking brackets and keep factoring. Okay, interesting. Uh, ballots? Sorry. in bracket. Okay, yeah, we can probably factorize this. However, let's look back at the question. I mean, like, what would the factorization be? It would be something. Okay, that'd be a complicated factorization. I'm thinking there's probably a theorem. I don't know if you guys have okay. So this question, as you can see, like the most prominent feature, right, um is the fact that it has an exponent that's really large, right? So it's raised to 12 16. Like guys, you probably have never seen exponents this high before. But do we know a tool that helps us, just like nukes all the exponents? Does anyone know a tool that just nukes the exponents? Have you learned a theorem perhaps about exponents and prime powers? It's actually called the for well, it's called the FLT of Fermat's Little theorem. Have you guys heard has anyone heard the theorem before? Oh, I sent a direct message to Jackie. Oops. Fermat's Little theorem. Okay, that's totally fine. I'll go over the theorem with everyone, and hopefully once I'm done, uh, everyone can see why this is applicable. So it states that a to the power of p, p minus 1 is equal to 1 mod p. No, Josie, you're not allowed to use calculators. Does anyone see how this theorem relates to problem 2? Alicia, can you see how this theorem relates to helps us solve problem 2? Feel free to unmute and talk, guy, by the way, guys. Oh, okay. That's fine. Alicia, we're working on problem 2 right now. Uh, okay, I'll pick on someone else. Um, Miguel, can you see how the theorem I sent in the chat, a to the power of p minus 1 is equivalent to 1 mod p, relates to problem 2? Okay, can anyone else? Oh yeah. Uh, yes. Jackie said. Oh, by the way, Jackie, you're sending me direct messages. Feel free to just message everyone. Um, you said like 3 to the power of 7. 3 to the power of. Oh no. So 3 to the power of 17 doesn't have remainder 1. 3 to the power of 16 does. So as in the theorem it says a raised to the power of p minus 1. Yeah. Jackie, do you want to write out like a full solution? Yes. Thank you, Josie. 3 to the power of 16 and 2 to the power of 16 both have 1 mod 17. And what does it mean? Why does that help us solve this question, Josie? Why is this helpful? Well, let's see. If 3 to the power of 16 and 2 to the power of 16 both have remainder 1, residue 1, What is 3 to the power of 16 minus 2 to the power of 16? Josie, can you tell us what is 3 to the power of 16 minus 2 to the power of 16? Yes. Thank you, Amanit. Yes, the remainders subtract each other. So what does that mean? What is the remainder of 3 to the power of 16 minus 2 to the power of 16? Yes, correct. No remainder, 0, right? So what is the answer to this question? Is 3 to the power of 16 minus 2 to the power of 16 divisible by 17? Thank you, everyone. Okay, well, let me let me just ask everyone a new question to test each other's understanding, shall we? What about 3 to the power of 12 minus 2 to the power of 12? Is this divisible by 13? Josie, can you explain why this is divisible by 13? By the way, guys, feel free to unmute and talk. Yes, very good, very good. Precisely. Uh, well, because 3 to the power of 12 has residual 1, and then 2 to the power of 12 has, well, to be precise, we don't say it has no remainder, we say remainder is 0. It just makes it sound cooler, you know. But yes, so 3 to the power of 12 minus 2 to the power of 12 is equal to 1 minus 1, and as we all know, 1 minus 1 is 0. Very good. Let me ask another question. Now, what is the remainder of 3 to the power of 32 mod 17? So we know that 3 to the power of 16 mod 7 is equal to 1 mod 17. What is 3 to the power of 32 mod 17? Yes, thank you, Jackie. Uh, Jackie is correct in this case. It's actually equal to 1. Jackie, can you explain to everyone why it is equal to 1? Yes, that's correct. Because 3 to the power of 32 is equal to 3 to the power of 16 squared. And as we all know, 1 squared is equal to 1. Yes, very good. Okay, what about 3 to the power of 17 mod 17? Yes, correct. Because 3 to the power of 17 is equal to 3 to the power of 16 times 3 to the power of 1. And 3, as we all know, this is equal to 1 times 3 to the power of 1, which is just 3. Right, so I will write this working out. Does anyone have any question up to this point? All right, thank you. So yeah, this actually reviews to us something that's even more profound than just a to the power of p minus 1. This actually tells us that the the residue of a number a raised to the power of anything starts repeating. Now I'll let that idea thinking. It's actually a really profound idea that 3 to the power of 1 is equal to 3 to the power of 17. It's equal to 3 to the power of what's 17 plus 16? I'm bad at math. Oh, 43, right? Which is equal to 3 to the power of um 3 to the power of 43, which is equal to 3 to the power of 43 plus 16, quick math, 59, I think. Is it 59? Oh wait, 33 and then 49. Yeah. Um, right. It just start and the pattern just like goes on repeating forever. Right. And similarly, 3 to the power of 2 is equal to 3 to the power of 18. It's equal to 3 to the power of what's 18 plus 16? 34. Right? Like the remainders, or we also say the residues. They just with period repeat with period remainder of a power of n not p repeats with period p minus 1. Now this is a really profound result because well, it actually allows us to oh oh yeah thanks April. I should probably start a whiteboard. How do I Where's the whiteboard? Hmm. Sorry, April. Do you know how to start a whiteboard? Oh, down near the right hand. Cool. Uh, what's happening? Wait. Oh, I think I just clicked out of it. Okay. So, next to the end meeting button. Sorry, do you mind just starting the whiteboard for me? Thank you. Um, yes, it works. Thanks. Um, yeah. Please don't draw on the whiteboard. Thank you. So yeah, as I was saying, 3 to the power of 1 is equal to, well, we say, so we use 3 horizontal bars to say equivalent because, they're not actually equal. It's just they have the same remainder. So, and we can probably start with 3 to the power of 0. It's equal to, 3 to the power of 16 equal to 3 to the power of 32 equal to 3 to the power of 0 is just equal to 1, right? So, mm, right, it just repeats with period 16. And it's not just the prime 17, it's not just the prime 17. If you change 17 to 13, pattern still holds, except now the period is 13 minus 1, which is 12 instead of 16. Uh, yeah, very good question, Josie. Um, for Fermat's little theorem to apply, yes, the modulus has to be prime. However, there is another theorem that generalizes the theorem to non-constant numbers as well, which we'll go over later. For now, yes, it has to be prime. And this is really useful because, it means that, well, it actually doesn't matter how big the exponents are, right? We can always take exponent modulo 16, right? For example, even if the exponents aren't 16 here, maybe there's something ridiculous like, let's see, uh, what's 16 times, oh yes, even if it's 3 to the power of Oh, sorry. 3 to the power of 106 1600, right? Even if it's like 100 times bigger, this rule still applies, right? And this theorem just allows us to break down ridiculously large exponents into really small exponents by taking modulus p minus one of the exponents, right? Um, okay, let me ask a final question to test our understanding on the theorem. 3 to the power of 1602 minus 2 to the power of 1601. What is this? Mod 17. Okay, we have an answer for one. Do we have any other answers? Anyone else? One guess on one. Any other guesses? All right, let's try this out. So we know that we can just take mod 16 of the exponents. So if we take mod 16 of 1602, it just, well, 1600 is obviously divisible by 16, so it just becomes 3 to the power of 2 minus 2 to the power of 1, which is equal to 9 minus 2, which is equal to 7 mod 17. Does everyone understand that? Mac, you unmuted yourself, by the way. That's fine. Yeah. So yeah, pretty useful theorems. Oh, one moment. Wait, let me just take a screenshot of the whole thing. So, um, hmm, one moment. Sorry, April. I can't really take screenshots right now. Um, it might just yeah. So, we might just have to deal with it. Anyways, so sorry for the interlude. Going back to this question, as I was saying, um, as I was saying, yeah, and this theorem called Fermat's Little theorem allows us. Uh, can you please don't touch the whiteboard, please? Whoever is moving this three, thanks. Yeah, this theorem just allows us to break down ridiculously large powers like 160. Actually, it can even be 16000002, right? It can just this theorem just obliterate large powers. Pretty cool, right? All right. Let's move on to let's move on to question 3. So question 3 uses a different theorem named Chinese remainder theorem. Has anyone heard of this theorem before? Okay, that's totally fine. Chinese remainder theorem, once again, another theorem that totally obliterates, well, actually, Chinese remainder theorem is even more powerful. it can obliterate large numbers. It can also construct large numbers. Let's see how it works. Basically, the statement states that, okay. So suppose you imagine a number, all right? So suppose we have an unknown number x, right? And x satisfies the following property. X is equivalent to, a mod, let's say remainder 1 mod quotient 1, right? So one example could be maybe x is, and then x is equal to, I don't know, x is equal to 2, 12, 16, right? So for example, e.g. 2, 12, 16 is equal to, so R1 is equal to 1 and the residue Q1 is 17. And that's one example. But it can be anything. It can be any Q and any R. It doesn't matter. Like it can be like 2 mod 17. It can be 3 mod 17. Q doesn't even have to be prime. It can be, Q can be like 6 or 10. Then X is equivalent to R1 mod Q1 is equal to R2 mod Q2 is equal to R3 mod Q3. Then all the way, we can have like 100 different equations here, and everything even matter a thing. Chinese remainder theorem states that no matter how many pairs of R1 and Q1 we have here, as long as they satisfy GCD, so as long as they're pairwise coprime, does everyone know what coprime means? So coprime means that their greatest common divisor is 1. So they don't have any common factors. No, not quite, not really divisible by one another. For example, 4 and 6. Now, what is the greatest common factor of 4 and 6?
2.
Yes, thank you. Yeah, right. So are 4 and 6 coprime?
No.
Yes, thank you. Right, they're not coprime because their greatest common divisor is equal to 2, which is greater than 1. Right, as you can see, 4 doesn't divide 6, but and 6 doesn't divide 4, but still they're not coprime. So coprime means numbers like, for example, 5 and 6. Right, 5 and 6 are coprime because their greatest common factor is 1. Notice that those numbers don't have to both be prime. Like for example, 6 is not prime, right? They can both be composite, in fact. For example, we can have 10 and 9. Now they're both composite, but their greatest common factor is still 1, so we still call them coprime. So yeah, suppose that Q1 all the way to Qn are pairwise coprime, which means that any 2 of them are coprime. So Q1 is coprime with Q2, Q1 is coprime with Q3, Q2 is coprime with Qn. All of them are coprimes. Then Chinese remainder theorem states that there exists a unique solution. There exists, the symbol means there exists a unique solution X mod Q1 times Q2 times Q3 times all the way to Qn. Sorry, apologies for bad handwriting. But yeah, notice that Q1 times Q2 times Q3 all the way to Qn is a ridiculously large number, right? Maybe I should write X better. X. Cool. There we go. Yeah. And this is something that's really profound because it's a unique solution. So not just there exists a solution. There are no 2 solutions. There's only 1 solution to this. Modulus Q1 times Q2 times Q3 times Qn. Now, that's a lot of algebraic symbols, so let us just do some examples. Let's start with x is equal to, I don't know, 1 mod 2 is equal to 2 mod 3, and then 3 mod 5. Now, can someone tell me, can someone give me an example of x that would make this work? Feel free to just try and error. Like, try the first 30 number, you're gonna find it eventually. Yeah, 30, let me check. 35, yeah, it's odd, and 2 mod 3. No, not 35, sorry. Because 35 is 0 mod 5, so not quite. 23. Oh, let me check 23. Yes, 23 works. Thank you. Right, so 23 works. And you can actually you can actually check after class. 23 is the only solution between 1 and 30. Yes, 1 and 30. Now you're gonna encounter more solutions if you go beyond 30. I'm gonna write them out here and see if you can discover the like the pattern. Does anyone notice what I'm doing here? Yeah, difference of 30. Very good. Yeah. So they're all equal to 23 mod. Very good. Yes, which is the product of 2 times 3 times 5. Yes, the lowest common multiple of 2, 3, 5. And since we know that all of them are co-prime, the lowest common multiple is just equal to the product of all of them. So yeah, so you can so x equivalent to 23 mod 30. Now, numbers satisfying x 23 mod 23 mod 30 are all solutions to the set of to the set of equations. Furthermore, they're the only solutions. Like all solutions satisfy all solutions have residue all solutions have remainder 23 when divided by 30. And furthermore, all numbers that have remainders 23 mods when divided by 30 are solutions to this set of equations. Now that's pretty cool, right? You can think of Chinese remainder theorem as the theorem that combines all of these equations, like combines all of these, Q and Q combines all of these quotients into a big quotient. Like you guys see the pattern here, like we basically we got all three of these equations, and then like we put them through a hydraulic press, right? We have like a hydraulic press, and poof, CRT by CRT they get turned into 23 not 30. We compressed all three equations into one equation. Now, this one equation is equivalent to the combination of all three of these equations. And in fact, you don't it doesn't have to be three. Like you can go on indefinitely. I mean, you can maybe add like one more, I don't know, 4 mod 7, right? And you would get a new result here. I don't know what that would be. Let me think. That would be something like, oh yeah, 53. New result. Wait, does 53, does it work? Yeah, 53 just works. And can someone tell me what the mod is here? we just added a new equation for mod 7. Will be the mod on this side. Yes, thank you very much. 210, which is 2 times 3 times 7 times 5, right? We got a hydraulic press called a CRT, and we pressed all four equations together and give us 53 mod 210 as the combination of all four equations. So yeah, that is pretty cool. Now let us go back to question 3. Okay, oh my God. Okay, question 3 is almost too easy now with the tools that we have. All right, quickly, can someone find the number n such that 2 divides n? So, uh, yes. Oh, actually, yes, 8 just works. Very good. So 8 works. Now let's make it a bit harder because we just learned CRT. Mm, can someone find me all numbers n such that they satisfy those three equations? I want someone to describe all the number n that satisfy those three conditions. Yes, thank you, Jackie. You just add 30. So n is equivalent to 8 mod 30. The trick to this question is you will write all the divisibility conditions as remainders. So n is equivalent to 0 mod 2, n plus 1 is equivalent to 0 mod 3, n plus 2 is equivalent to 0 mod 5. And then you get plus 1 and plus 2 to the other side. So you get n is equivalent to 0 mod 2, n is equivalent to -1, which is 2. The n is equal to -2, which is 3 mod 5. And then you notice, oh, well, you can apply Chinese remainder theorem, right? You can compress them using hydraulic press into 8 mod 30, which is the answer we're looking for. All right. Is everyone following? Does anyone have any questions to ask at this point? Very well. Moving on. Question uh, question 4. Okay, so question 4 is a bit hard. But let me give you a reminder. Okay, pun. Let me give you a reminder here that we just learned the Chinese remainder theorem, which states a solution exists. And you don't actually have to find the solution every time. Sometimes, as in the case of this question, you just need to prove that a solution exists. You don't need to find out what that solution is. So yeah, I'll give us 2 minutes until 7:15 to think about this question, and then I'll start asking for ideas. Arbitrary means it can be anything. Like it can be any length. It can be like I don't know, one number long. It can be 100 number long. It can be 1,000 number long. It can be like 1 million 1 million positive integers. It can be anything. Okay, it's 7:15. Does anyone have any ideas? So let's start from simple first. As I said, this question uses Chinese remainder theorem. So can someone can anyone see how this question can be rephrased in a way such that it is written in terms of a bunch of equations? How do we rephrase it? How do we rephrase it in such a way that we can turn it into a system of equations? Adrian, do you have any ideas? Okay. What about you, Atom? All right. Okay. Let me try to explain. Let me explain this question. So the question asks us to construct arbitrarily long sequences of composite numbers. For example, one sequence I can think of from the top of my mind is say um, 8, 9, 10. Right? 8, 9, 10 are all composite. Right? So it's a sequence of 3 consecutive composite numbers. However, you can't continue this indefinitely because if you add one more number, say 11, you run into a prime, so it doesn't work. However, you can find a sequence of 4 consecutive composite numbers if you look into 14. Oh, wait, no, 14, 15, 16 doesn't work. What's the next sequence? 20, 21, 22. Oh, doesn't work either. Who can tell me what's a sequence of 4 composite numbers? Ah, yes, very good. Thank you. 24, 25, 26, 27. You can even go for longer. You can go for 28. Yes, that's 5. That's even better, right? Um, we just need to take so yeah, that's 5. However, you can't go for any longer because if you go the number afterwards is 29, which is prime, so it doesn't work. However, I claim that if you look far enough, if you look, you will eventually find a sequence of 6 consecutive composite numbers. And in fact, not just 6 consecutive composite numbers, but if you look far enough, you can find a sequence of any length. Right? If you can look far enough, you can find a sequence of 1 million composite numbers. And if you look further, you can find a sequence of 10 million composite numbers. And so on, goes on forever. Now, of course, it doesn't go on forever because eventually you will run into a prime number. Because as we all know, there are infinitely many prime numbers. But however, um, there's no limit to how long of a sequence you can make it. All right, cool. So it has been 5 minutes. So let me start giving out the solution. So as I said, the first step is to rewrite those in terms of bunch of modulus. So let's say, well, how do we know something is composite? We know something is composite if it's divisible by a number smaller than itself, right? So we say, okay, n is equal to 0 mod p1. Maybe p1, let's say p1 is just a prime. Yes, more than 2 factors. So let's say n is divisible by p1 and p1 is smaller than n. And then n plus 1 is divisible by P2. N plus 3, oh, not N plus 3. N plus 3 is divisible by P, N plus 3 is divisible by P3. And so on until suppose we're looking for, I don't know, maybe we want a sequence that's k plus 1 numbers long, so we stop at k. N plus k is equal to 0 mod p k. I mean, cool. Yeah, so suppose we want a sequence that's, so yeah, can everybody see that, if all k of those equations are satisfied, then we have in our hands a sequence from n to n plus k minus 1. We have a sequence of k composite numbers. Can everyone see that? Right, because P1 divides n, and P2 divides n plus 1, and P3 divides n plus 2, all the way until n plus k minus 1. So all k of these numbers, and mind you, they're consecutive, right? All of these numbers are divisible by a number that's smaller than them. So if we can get all k of these equations working, then voila, we have a sequence of k composite numbers. Is everyone following? Does anyone have any questions? Okay, cool. So yeah, nice. Now we have, well, a bunch of equations. Can someone tell me why it is guaranteed that we can find a solution? Cian, can you tell us why by Chinese remainder theorem why we're guaranteed to find the solution? Can anyone else tell us a solution? So yeah, type the full solution in the chat. Well, so as I said before, Chinese remainder theorem guarantees that if we're given a bunch of equations and then and then all the quotients here are coprime, which they are because I carefully picked all of them to be prime numbers, to be different prime numbers, right? So they're all coprime, and so therefore, by Chinese remainder theorem, we're guaranteed to have a solution. A unique solution, in fact, but we actually don't even need it to be unique. We're just Chinese remainder theorem just tells us there is a solution. Now, it doesn't tell us what the solution is, but that's all right because we're not asked to find a solution. We're just asked to prove that a solution exists. And then because the solution exists, therefore, the sequence, because the solution exists to the sequence of prime, therefore, n plus 1 dot 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 all the way to n plus k minus 1 are all constant numbers, right? Because they're all divisible by by at least one prime. Now, it might be a bit tricky if you got a number that's too small, and so maybe, I don't know, n plus 2 is equal to p3, but you can solve that easily by just adding p1 minus p2 minus p3 plus minus times pk to everything. So yeah. How's everyone doing? That's totally fine. Thank you for asking the question, Atom. Um, can you tell me where I stopped making sense? Okay, I will go through the whole thing step by step again. Can we all agree that if P1 divides n, P2 divides n plus 1, P3 divides n plus 2, and so on, then n plus 1, n plus 2, all the way until n plus k minus 1 are all composite. Can we agree that if this is true, it implies that the sequence are all composite? Is our Thank you, Jackie. Atom, do you understand this part? Okay. So do you know what composite means? Like, what does it mean for a number to be composite? What does it mean? Yes, it's pretty much non-prime. What does it mean to be prime? Yes, very good. So, do you agree that a number is composite if and only if it is divisible by a factor that's not itself a one, right? Because a composite number is the opposite of prime, right? So if it is divisible by a factor that's not itself a one, then it is composite. Very good. So yeah, if P1 is not equal to 1 and it's not equal to n, and it divides n, n must be composite, right? And similarly, if P2 is not n plus 1 yet it divides n plus 1, then n plus 1 must also be composite, and so on and so forth for all of those numbers. Very well. So I hope everyone is following with this part. So now this question just becomes, can we prove that there exists an n such that all of those equations are correct? And it turns out that we can just quote the Chinese remainder theorem, which states that such an n exists. Such an n exists. Such an n exists by CRT. Therefore, we're done. No, we don't need to find out what that n is. We just need to know that that n exists. Is everyone following? Atom, do you understand this part? Yeah, thanks. So yeah, that's the full question. Such an n exists by CRT, and since this exists, therefore those numbers are composite, and we're done. There's a small caveat where we must prove that n is not equal to p1 and n plus 1 is not equal to p2 and n plus 2 is not equal to p3. But that part is quite easy because remember that if n is a solution, if n is solution, then so is n plus p1 times p2 times p3 times all the way until pk, which means that we can basically make our n ridiculously large, so large such that n is larger than all of those primes here. And so if it's so much larger than all of these primes, then obviously we don't need to worry about it being equal to any of them. So yeah, that's this question. All right. Question 5. Oh, question. I have never seen question 5 before. This will be fun. All right, same as before. 2 minutes, except that after 2 minutes, I'll also be joining in your discussion because I actually haven't seen this question before either. So yeah, have fun. Very point with integer coordinates just stands a tree. All right, 2 minutes up. Once again, does anyone have any ideas? Or like, does anyone want me to help explain the question to them? Does everyone understand what the question is asking for? What GED? Oh, I think it's GCD here, and GCD means greatest common divisor. Yes, it means a square shape. So, you know, if we draw the graph, oh, there's a grid in the background. That's nice. So yeah, we have like a tree over here, a tree. Oh, let me just make it straighter. Okay. You know what? I'm not really good at straight lines. So yeah, imagine the grid, right? And we have a dot. We have a tree at all of these dots here. We have a tree 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 here. However, notice that if you're standing in the origin, you can't really see this tree, right? Because it is blocked by this tree over here. Now you can see this tree, but you can't see this tree over here because it got blocked by this tree here. Now similarly, you can see what other see? You can see this tree, but you can't see any tree behind it once again. Like what's the tree behind this one? This one is at 3, 2, so we have 4, 6. Where is 4, 6? Yeah, you can't see this tree because this tree got blocked by this tree over here. And so the question is asking, prove that there exists a square of trees, all of which are blocked. Now, more precisely, a tree is blocked when its x coordinate and its y coordinate are not co-prime. So if there, when its x coordinate and its y coordinate have a greatest common factor that is not 1, then that tree is blocked by another tree in front of it. So you want to find a square such that all the trees are blocked. All the trees, all the points in that grid satisfy that their greatest common divisor is greater than 1. Now, an insight to this question is that, well, actually this whole analogy of trees is just meant to trick you up. Let's just ignore all those trees because trees are difficult. It's much easier to imagine the numbers. So the question is asking you for prove that there exists. Like maybe the first number is m, the second number is m plus 1. Oh, a sequence would be like this. So m plus 1, m plus 2, all the way until the last sequence, last number, which would be m plus n minus 1. So all of those n numbers satisfy the condition such that if you take any two numbers from the sequence, like if you take m and m plus 2, wait, hold on. Oh. Oh, okay, wait, not quite, not quite. Sorry. I made a mistake in interpreting this question. Let's reinterpret it. So you have the points x1, y1. So Okay, you have two sequences, x, x plus 1, x plus 2, x plus n plus 1. Oh, n minus 1. And you have another sequence, y, y plus 1, y plus 2, y plus n minus 1. Right. So the correlation is, imagine a square such that, imagine a square. Right, that's fine. Thank you, I'm on that. The idea is that imagine a square such that its bottom left corner has the coordinate xy. And it's n units long. So what's the coordinate of the top left corner? Does anyone know what the coordinate of the top left corner is if the square is n units tall? Yes, very good. Thank you. X, y plus n minus 1. Now what's the coordinate here? Yeah, x plus n minus 1, y. And here it's x plus n minus 1, y plus n minus 1. Very good. So yeah, for any points inside the square or on the border of the square, its x coordinate has to be picked from the first sequence, right? Its x coordinate has to lie between x and x plus n minus 1. And its y coordinate has to be picked from the second sequence, right? Its y coordinate has to be picked from y, between y and y plus n minus 1. So we're asked to prove that there exist two such sequences, such that if you pick a number from the first sequence, let's say you picked A from the first sequence and B from the second sequence, then they satisfy GCD AB greater than 1. So A is from this and B is from this second sequence. Now, can someone give me an example of two such sequences? Maybe starting with like a really small n, like maybe starting with n is equal to 2. Right, give me two sequences, each containing two numbers, such that if you choose A and B, you will always get two numbers that aren't coprime. Oh, let me give you guys an example. 4, 5. What do I pick here? Wait, doesn't hold on. 4 and 5 doesn't work, right? Wait, let me pick a better number. Hmm. Okay. 6, 7? No, 6 and 7, not ideal. Let me. Well, actually, I need to think about those too. It's not as trivial as I thought. 14, 15. 2, 7. Well, okay, this question is a bit hard. Oh, 66. I got it. 66. Cool. Uh, where does 60? Hold on. Hey, that doesn't work. What went wrong? Oh, 33, but 30. This question is a bit, I must admit, is a bit harder than I thought. Um, oh, it can't be mod 34, it has to be mod 35. Hmm. Ah, sick. Oh, yeah, good question. Why did I choose 14 and 15? Hmm. the the idea here is I want to find two numbers such that they each have two prime factors and they each have two different prime factors. So 14 is 2 times 7, and then 15 is 3 times 5. Um, yeah, that's why I chose 14 and 15. And now I'm trying to find a number such that y is divisible by 2 times 3, and then y plus 1 is divisible by 5 times 7. But I'm having a bit of troubles, so I kind of need you guys' help here. Help me, guys. um, oh, we just mm, we're just trying to find a number such that it's 0 mod 6 and 34 mod 35. Um, because it just because we know such numbers have to exist. I'm just trying to find what number that number is. Mm, okay. I can't do arithmetics at like 8 o'clock. Is anyone good at arithmetics and can tell me like what why is? Ah, oh, and what's 282 divided by 35? Well, doesn't actually matter, guys. Anyways, here's the magic of Chinese remainder theorem. I have no fucking sorry. I have no clue what y is, but it doesn't matter because I know y exists. So yeah, let's just be cheeky here. I can't be bothered to find what y is. I just know that y exists, right? Because 6 is co-prime to 35. So y has to exist by Chinese remainder theorem. And so 14, 15, y plus 1 just works. Don't ask me what y is. I have no idea. But it just works. This is like magic, you know? You know what I mean? It's, I'm sorry if it's like a bit sus, but like, does everyone see how Chinese remainder theorem tells us that y has to exist? even if we can't find what y is. Yeah, it's fine. I'll start from the beginning. So like, I'm just trying to start with some simple examples first to like get our minds around, get our heads wrapped around this question. Right. So let's start with a sequence that's really short. Okay. I mean, when it is one, it's pretty trivial. We just need to find two numbers such that they're not co-prime. Any numbers will do that. Maybe like 4 and then 6. And that's why n is equal to 1. Now, n is equal to 2, a bit trickier. But let's say the first sequence is 14, 15. Right. Let's say this first sequence is 14, 15, and I don't know what the second sequence is. Let's just say it's y plus 1. All right. I'm trying to find a y such that GCD 14y is greater than 1. GCD 14y plus 1 is also greater than 1. GCD 15y is greater than 1. GCD 15y plus 1 is greater than 1. Right? If all four of these conditions are satisfied, then we're done. We just find a sequence. We just find two sequences that just work, right? And we're not done with the question, but at least we found two sequences that work. Right? Jackie, do you follow? Cool. So what can GCD 14y be? Right? I mean, well, GCD 14y obviously has to divide 14. Um, so it's either 2 or 7. And I don't actually care whether it's 2 or 7. Let's just say it's equal to 2. Why not? Uh, I'm tired. I'm bored. And then 14y plus 1. All right, it has to be either 2 or 7. No idea whether, well, it's 2 before. And we know that y and y plus 1 are co-prime. Well, if y is divisible by 2, then y plus 1, they can't both be divisible by 2, right? Because y plus 1 is like, if y is divisible by what, 2, then y has to be even. Therefore, y plus 1 has to be odd. So this has to be equal to 7. Now, similarly here, 15y. So it's either 3 or 5. I'm just going to say it's equal to 3 and get the next one is equal to 5. Right, I'm just picking the numbers randomly here. Right, is everyone following? Cool. Cool. So now we want a number such that y is equal to 0 mod 2, y plus 1 is equal to 0 mod 7, y is equal to 0 mod 3, y is equal y plus 1 is equal to 0 mod 5. Is everyone following? Oh, and we can rearrange it such that we get -1 on the side. Cool. Is everyone following? Nice. Now, what does the Chinese remainder theorem say, guys? Like, what if we use the hydraulic press of Chinese remainder theorem? What does it tell us? Oh, simple. Chinese remainder theorem tells us that y has to exist. That's it. Y has to exist. Notice that it doesn't tell us what y is, but it doesn't matter because in this question, we're just asked to prove that there exists y. And Chinese remainder theorems tells us this is true. There does exist a y. So we're done. Is everyone following so far? Cool. Yeah, except we're not quite done. We have only proved that there exists a sequence of well, we have only proved that it works when n is equal to 1 and when n is equal to 2. We still need to generalize this proof to like when n is equal to 3 and then 4 and then larger numbers. But yeah, it follows roughly the same idea. So let's just construct x such that it's divisible to 0 mod. So let's construct x such that it's divisible by a lot of things. To be precise, we want it to be divisible by how many things do we want it to be divisible by? Well, let's just say we want it to be divisible by n different things. Why not? Like Chinese remainder theorem never limits how big we can go. So the only thing limiting ourselves is our imagination. So let's just go big. Go big or go home, right? Let's do something that's like tremendously big. Right? So x is divisible by like n different things, right? And let's say x plus 1 is divisible by even more things. It's also divisible by n different numbers, and all of those n different numbers are like different from the ones that divide by x. So we get like it's divisible by n plus 1, x plus 1 is divisible by n plus 2, x plus 1 is divisible by n plus 3. Dot 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 all the way until it's divisible by 0 mod p 2n. Right? And we'll keep going for like x plus 2, dot 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 all the way until x plus n minus 1, which is divisible by a bunch of it's divisible by like n more primes. Right? So we're basically using like n times n different primes here. Right? So the basic idea is x plus 1, x plus 2, all the way until x plus n minus 1 are all divisible by at least n primes. And all of those n primes are different. Now, this is going to give us some x that's ridiculously large. And even if you use like all the computers in the world to search for it, you're probably not going to find it for like another 1,000 years. But it doesn't matter at all because we know that x has to exist. Right, and that's enough. We don't need to know what x is. We just need to know that it exists. And then similarly, we can construct y is equal to okay, maybe it's like tidier if we write out all the primes in like a square itself. Dot 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 pn. Now pn plus 1, pn plus 2, pn plus 3, dot 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 p2. Right, we're just writing out all the primes we're using, all n square of them. Right? If n is 100, we're using 10,000 primes. If n is 1,000,000, then we're using 1 trillion primes. It doesn't matter. We can go as high as we want. Pn squared minus n plus 3 dot Pn squared. Cool. And let's say x is divisible by every prime in this row. X plus 1 is divisible by every prime in this row. X plus 2 is divisible by every prime in this row, all the way until x plus n minus 1. And then y, we're going to do columns. Yeah, that's fine. Y is divisible by everything in this column. Y plus 1 is divisible by everything in the second column. Y plus 2 is divisible by everything in the third column, all the way until we get to y plus n minus 1. So all the x's are divisible by every prime in its row. All the y's are divisible by every prime in its column. Right? And we know that we can always find such x and y by Chinese remainder theorem. We don't know what x and y are. Right? Even for really small n, as you can see over here, I was like struggling to find what y is. But that's okay, because we don't need to find what x and y are. We just need to know that they exist. Right? And if you pick any two prime here, sorry, not prime. If you pick any two numbers here, like if you pick y plus 1 and you pick x plus 2, like maybe the coordinate is like x plus 2, y plus 1, right? You know that they share at least one factor, right? It's just the cell where their columns and rows intersect, right? They all share at least one prime factor. Now, if you pick y plus 2 and x plus n minus 1, they share this factor over here, right? And this applies to any combinations of x and y. And this has to, so yeah, that's it. That's the question. I think we're approaching the end of our lesson as well. I hope everyone had fun. I think if there's one takeaway from this lesson, like your takeaway should be how, we can break down very large things into very small things. Like for example, the first question, right? 16 maybe is a bit small, but we can even, right? We can do we can break down ridiculously large things into very small things. And we can also construct ridiculously small things. We can also combine a lot of ridiculously small things into a ridiculously large things. Like x and y here, probably in the order of x1 times, p1 times p2 times p3 times all the way until pn squared. That's like n squared different primes, right? That could be like 1 trillion different primes all multiplied together. And even if you use all the computers in the world, you're not going to find what x and y are before the end of the universe. But you know that they exist, and that's all that matters. So yeah, that's it for this lesson. All right, I will stay behind for 5 more minutes to see if there are any questions. Otherwise, feel free to leave.